Welcome back to another amazing session. Think to yourself for a minute. We've learned how to take the derivatives of so many different functions. Polynomials, rational functions, which are fractions of polynomials, trig functions, inverse trig functions, exponentials, and we've just missed one main family that we care about. Of course, you can always make lots of new families by combining these or taking all kinds of fancy other math. But from what you've learned so far, what is the big family of functions we haven't learned how to do the derivative of? Logs. That's right, logarithms, natural logs, common logs, log base 2, all kinds of logarithms. They are not just going to be good for their own sake, but once we learn how to take the derivative of a logarithm, it'll help us do all kinds of other derivatives as well. So this is why this section is both called logs and logarithmic differentiation, which will be using logs to help us out, turning complex operations into simpler ones. Okay, so hopefully you took a minute to watch the video on reviewing basic log properties, that warm up. Definitely all those main properties are going to be necessary, and the more that you know, the more things are going to make sense and the faster this will go. So you've had to review some trig, probably, maybe time to review some logarithms as well. But let's go ahead and jump straight on to the derivative. The derivative of natural log of x, I'm going to just go ahead and tell you it before we bother to prove it. The derivative of natural log of x is amazing for its simplicity. It is 1 over x. That is it. And maybe you thought to yourself, that something was missing in our derivatives. If you think about it, I can get the derivative, I can make a derivative be x squared by choosing something like x cubed. I can make a derivative be x to the negative 2 by doing like an x to the negative 1. But 1 over x is x to the negative 1. And x to the 0 is just 1. So it was kind of this missing piece, right? What function has a derivative of 1 over x? Turns out it's natural log of x. Yet another reason why the natural log is the best log, and that there's something really fundamental happening here. Okay, I want to add in this other piece. Natural log of x has a restricted domain. It is only defined for positive numbers. So how would I make it defined for all numbers? Well, I would just do the natural log of the absolute value of x. And the derivative of that, almost magically, is just 1 over x. So secretly, on this left side, we actually have an x greater than 0, because the domain is restricted there. Why is this true? Well, if we real quickly sketch this out, bloop, 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 and I sketch out a natural log, and an absolute value is just going to reflect it like this. So that negative numbers are treated like positive numbers. Not my finest. In fact, let me just go ahead and draw this a little better. Still not amazing, but slightly better. So notice that for a negative value in that absolute value, my slope is just the negative. So here I've got a positive slope, and here I've got the same but negative slope. 1 over x is an odd function. So it is actually doing the same thing, but rather instead of with its derivatives, it's doing it with its y values. The y values are the negative of each other. So it really does work out all nice and pretty just by symmetry. Okay, so what about some other base, like base 10 or base 2? What would that be? Well, it's almost the same. It's almost that nice, but it's a little bit messier. Let's go ahead and try to prove this, and then I'll fill in that one. If we can do it for base b, we can certainly do it for natural log of x, because that would just be base e. Okay, the one thing I really know about a logarithm to define it is that it's an inverse function. So let's actually talk about this in terms of its inverse. This means that b to the y is equal to x, right? B to what power is x? That's what this is saying. That's what it means to be an inverse. This looks a little messy, but now that we can do implicit differentiation, we can find dy dx. Let's go ahead and do it. The derivative of b to the stuff is natural log of b times b to the stuff. But now I need to do the chain rule on that stuff, so that's dy dx. All right, the derivative of the right side is just 1. Now all we gotta do is solve for dy dx. Not too bad, just divide. 1 over natural log of b times b to the y. This is okay, but we really don't want a y in there, right? We really want to have an x. So it'd be nice if I had some way of writing b to the y using an x. Oh wait, I do. B to the y equals x. So this is just 1 over natural log of b times x. Ta-da! That's it. Let's write that up here. 1 over natural log of b times x. All right, that is my log base b. Notice what happens if that b is an e. If it's a natural log of e is 1. So we actually just proved both those lines together. We showed that the natural log of x has a derivative of 1 over natural log of e times x, but that's just 1 over x. And this is our fun formula for any base. Okay, let's give this a try with a couple of quick examples. Maybe pause, maybe see if you can do these on your own, but I'm going to go ahead and cruise through these. This first one is fairly straightforward, I think, because we're just using that formula. So this is log base 2. So y prime is equal to 1 over natural log of 2 times x. Ta-da! That's it. Oh, I got one snuck over here on the right. So y prime, this now looks like a chain rule. So let's take care of that square root first. A square root, you can write this a number of ways, but its derivative is going to be 1 over 2 square root log of x. Remember that log is a common log. Next up, we have to multiply that by the derivative of the inside. So the derivative of a common log is going to be 1 over natural log of 10, because that's that hidden base on a common log, times x. Actually doesn't clean up that much. So I'm going to leave it like that. Great. So that was both a chain rule and a common log, a log base 10. Okay, I like this next one a lot. Give it a try if you haven't already, but let's go through it. Y prime is equal to, the negative's going to hang out. It's just a constant multiplier. Natural log of stuff says, if I take its derivative, I got to put all that stuff on bottom. So this is the chain rule again, but now instead of an x, I'm putting that whole cosine of x on bottom. Okay, so derivative of natural log of stuff is 1 over stuff. Times, well, now I need the derivative of the inside. The derivative of the inside is negative sine. Derivative of cosine is negative sine. Now maybe you see this. If I simplify this, I get positive sine over cosine. This is nothing more than tangent of x. How cool is that? Who would have thought? Right? This is the kind of question that comes up in Calc 2 a lot. Here we find derivatives. Often in Calc 2 you're asking, well, what function has this derivative? So what function has a derivative of tangent of x? Negative natural log cosine of x. Okay, notice we just did two different chain rule problems that looked a little different depending on if the log was on the inside or the outside. And we got a tangent of x out. Okay, a couple more to go. Now it's a mix of chain rule and product rule. So my derivative, y prime, looks like I'm going to get a 1 over stuff. But my chain rule says multiply this by, oh, probably something big. Something with the chain rule. So 1 times e to the x plus, leave the x alone, derivative of e to the x is e to the x. Oh, I can't help but simplify this a little bit. Notice I've got an e to the x here, and I can factor out this e to the x. So this whole thing, if I simplify it, all those e to the x's are going to cancel when I factor out that e to the x and cancel the thing on bottom. So this is really just 1 plus x over x e to the x. Not so bad at all. Okay, just 2 more to go. These are a little bit more abstract, and that's on purpose. That's where this is going. So, y prime of natural log of some function. I don't even know what it is, but I don't really care. This is the expressive power of calculus and your ability to work with functions. So it's going to be 1 over stuff, because the derivative of natural log is 1 over x, so f of x goes on bottom, times, chain rule says take the derivative of f, whatever this weird function is. Well, the only way I know to write that, because I don't know what it is just f prime. Sometimes we'll even shorthand this as just f prime over f. Okay, you'd be surprised how often this comes up, the natural log of f, because we choose to take a natural log of both sides to make our lives easier. So if I want to take the derivative of natural log of f, I just get f prime over f using that chain rule. Almost the same thing over here. Looks like I get this derivative. Now I'm not going to write y prime now because y is not on the left. I'm taking the derivative of this whole function here. So I don't want to write y prime equals. Y prime is some other thing. So this is going to be this whole derivative equals 1 over y times the derivative of y. Well, that's just either dy dx, or let's go ahead and write y prime this time. So this is just y prime over y. Very cool. Same thing as before. So where this is going is in the next video, we will take the natural log of both sides and we'll have something like a natural log of y on the left. And when we take its derivative, we'll get something like this. And then we'll solve for that y prime. Super cool. Hopefully that was good practice. And then we'll do some really neat stuff in the next video.